Good morning. Okay, we're going to look at section 9.3. We're looking at double angle and half angle identities. And this is from the OpenStax College book, which is a free resource. Okay, now, so what we're trying to figure out now are identities that look like this. Sine of 2 theta equals what? Okay, so this is not 2 times sine theta for sure. All right, and we could figure that out pretty easily if we think about the example. Oh, I don't know. How about sine of pi over 3, which is, if we think about it, 2 times pi over 6. So if we said that that was 2 times sine of pi over 6, I think we can see how it would be wrong because sine of pi over 6 is what, 1 half? So this is 2 times 1 half, which is 1. And sine of pi over 3 is root 3 over 2, which is definitely not 1. Okay, so where did we make the mistake? Just like I said earlier, you cannot factor out the 2 like that. So how do you figure out sine of 2 theta? All right, well, we already, if you think about it, we already looked at sine of a plus b identities. And so we can use that same idea. Let me write it down again. All right, so we had sine of, let's say, alpha plus beta. If you remember, sine of alpha plus beta, you change your trig function so that's sine alpha cosine beta plus sine beta cosine alpha. All right, so that was what we did in section 9.2. So if I want to do that same thing, but this time let's keep the same angle. What I mean by that is, let's say sine of theta plus theta. I mean, that is sine of 2 theta, right? Sine of 2 theta is theta plus theta. So now if I plug that in, I get sine theta cosine theta, right? I get sine of the first angle, cosine of the second angle, not equals here, but plus sine of the second angle, which is theta, and cosine of the first angle, which is theta. Okay, so then I get, well, I have the same thing twice, so that's 2 sine theta cosine theta. And there's my first double angle identity, okay? So we can write that down, the double angle identities. And I'll go ahead and give you all three of them. 1, sine 2 theta is 2 sine theta cosine theta. All right, cosine 2 theta actually has more than one formation. So you play the same game, except you use cosine alpha plus beta. And let's do it real quick. All right, so I'm going to come over here on the side, and let's think about cosine 2 theta. So I'm going to apply again cosine theta plus theta, right? And so if you remember how that works, you keep the same trig function. So this is cosine theta minus sine theta sine theta, right? That's the cosine of alpha plus beta identity is cosine alpha cosine beta. Change your sign in the middle. Sine alpha sine beta. Okay, so then that means one way that this thing simplifies is cosine squared, right? Cosine squared, cosine times cosine, cosine squared, minus sine squared, sine times sine, which is sine squared, right? So this is cosine squared theta minus sine squared theta, like that. Okay, but notice though, cosine, anytime you see a cosine or a sine squared, what should instantly jump out at you is the Pythagorean identity. And remember the Pythagorean identity, cosine squared plus sine squared equals 1. So if I do some algebra on that, cosine squared is 1 minus sine squared. Remember doing that? So I could come in and replace cosine squared with 1 minus sine squared. And if I do that, I get my next identity, which is going to be cosine 2 theta is 1 minus 2 sine squared theta. Okay. The other way I could do this is starting from that equation. Instead of replacing cosine with sine, I could replace sine with cosine. So if I come up to my Pythagorean identity, and if I had solved for sine squared instead of cosine, that's 1 minus cosine squared. Alright, so then I could say that this is cosine squared minus 1 minus cosine squared. And you distribute your negative and rearrange your terms, and you end up with 2 cosine squared theta minus 1. So cosine 2 theta has 3 different forms, and depending on the context, one could be maybe more useful than the other. Okay? Alright, now the third one, tangent 2 theta. Well, remember tangent of a plus b was what? It was tan a plus tan b divided by 1 minus tan a times tan b. So if I replace a and b with thetas, you end up with 2 tangent theta over 1 minus tan a times tan b. So this is tan theta times tan theta, tangent squared theta. These are my double angle identities. And they're pretty useful. They will show up a lot if you do enough trigonometry and calculus. Alright, so let me give you an example on when you would see this or how it would work. Alright, so this is example 1 from the text. And it says, so given tangent theta is negative 3/4 and theta is in quadrant 2. And I believe we used this symbol before, but if we haven't, this means element of. And so what it's saying here is theta is in quadrant 2, and that's just a much quicker way of saying it if we know that symbol. So given tangent is negative 3/4 and we're in quadrant 2, find I want to know sine of 2 theta. Okay, not a big deal. All we have to do is apply our identity. So I know that sine of 2 theta is 2 sine theta cosine theta. Right, so it relates to you see why it's called double angle? Because it's 2 times theta. The angle is twice as big in the sine 2 theta as it is in, for example, the tangent theta. And that's something we know. Okay, so if we know tangent, can I figure out the missing parts? The sine and cosine are the missing parts. Yeah, we can do that. We're in quadrant 2. So here's my angle theta. And I know 2 things about this triangle already, right? Tangent is opposite over adjacent. Right, so opposite side is 3, adjacent side is 4. We use Pythagorean identity. And remember 3, 4 is a very common right triangle. It's a 3, 4, 5 triangle. All right, and if you don't remember that, that's okay. Just remember 3 squared plus 4 squared gives you 25, which is 5 squared, and that's how we figured that out. Alright, so from there, I can identify my missing parts. I know then that sine is opposite over hypotenuse, and cosine is adjacent over hypotenuse. But don't forget, we're in the second quadrant, and cosine is what? Negative in the second quadrant here. If we wanted to be technical, maybe we could say, if you think about where that point is, that's the point in negative 4 in the x direction, 0 in the y. So maybe it'd have been smart to say this side length is not 4, but the side length is negative 4. If we did that, it would actually help us figure out the signs appropriately here. But we could just remember we're in the second quadrant, so cosine's negative. Okay, so from there, it's just a matter of multiplying. Let's see, my denominator is going to be 25. My numerator is 2 times 3 times negative 4, which would be negative 24/25. There is my sine 2 theta. And I hope that makes sense. Okay, now for part B, I want to find cosine 2 theta. Alright, now I could do this, now that I have sine 2 theta, I could build a new triangle for 2 theta. But I'm not exactly sure, I'd have to think about it for a little bit, what quadrant 2 theta is in. If theta 1, if 1 theta is in quadrant 2. Why don't we just stick with our identities? Because we know, we have several ways we could do this. We already know sine and cosine, so what if we just said cosine squared minus sine squared? What if we just did that? Okay, so if I did that, let me think. Sine, again, cosine was negative 4/5. So I have negative 4/5 squared minus sine squared was, or sine was 3/5, so I have 3/5 squared. So that's going to be 16 over 25 minus 9 over 25, which gives me, what is that, 7 over 25. There's my cosine 2 theta. And realize I don't even have to worry about positive or negative here. The identity helped me figure that out without me even thinking about it. Right, so this is positive 7/25. Okay, so I think we could figure out now what quadrant I'm in. If sine 2 theta is negative, cosine 2 theta is positive. It didn't ask for this, but I'm just trying to reason out here. That would mean 2 theta would have to be in quadrant 4. It would have to be in quadrant 4, right? Sine's negative, cosine's positive. And if we look at tangent, so part C, tan 2 theta. And since I'm in quadrant 4, I expect this to be negative, right? Let's see, what was tangent again? Back at the beginning, tangent was negative 3/4, and I'm using this identity here, 2 tangent theta over 1 minus tangent squared. So all we have to do is just plug that in. So again, I'm saying 2 tangent theta over 1 minus tangent squared theta. And so if I plug in my values, I get 2 times, we said tangent was negative 3/4 over 1 minus negative 3/4 quantity squared. All right, and so that's going to be, let's see, negative 3/2 over 1 minus 9/16. So that's negative 3/2 over, let's see, 16/16 minus 9/16 gives me 7/16. And remember, dividing by a fraction is the same as multiplying by its reciprocal. So the same as 16/7. Here, the 2 and the 16 cancel out, and that would negative 24 over 7. And there's my answer. And I think this makes sense because notice I could have also said, so let's call that 1. 2, I could have said that, remember, tangent 2 theta is the same thing as sine 2 theta over cosine 2 theta, right? Quotient identities. And we already figured out both of those. We said that sine 2 theta was negative 24 over 25. We said cosine was 7 over 25. So since I'm dividing, I'm just going to go ahead and make that a reciprocal, 25/7. And so when you multiply that out, you get negative 24/7. But I wanted to illustrate algebraically how the identity would work. Okay, I hope this makes sense. Okay, now let me show you an example on how something like this could be useful. So this is example 2. And I want to write cosine 6x in terms of sine of 3x. Oh, not sine. Let's do cosine again. Okay, so I want to rewrite cosine 6x as cosine 3x somehow, right? That's my formula. Okay, so can I do this? So I start out with cosine 6x, and I recognize that this is cosine 2 times 3x. Okay, so 3x actually is playing the role of theta here, which makes sense then how we're going to have an expression of cosine 3x. Does that make sense? Cosine 6x is the double angle, or 6x is the double angle of 3x. Okay, now can I write cosine 2 theta simply in terms of cosine theta? Yes, we can. If you want to go back and look at our list, because we had 3 for cosine 2 theta. Notice cosine 2 theta is the same thing as 2 cosine squared minus 1. I think that's the one we're going to want to use. Okay, so here I have, let me say it again, 2 cosine theta squared minus 1. In this case, what is theta? What do we say theta was? Theta is that 3x. Right? That's your theta. The 6x is 2 theta. Okay, so there's my answer. I've rewritten cosine 6x in terms, cosine 6x in terms of cosine of 3x. Okay, and that's why these double angle identities are helpful. They help us go from potentially large angles down to smaller ones, or vice versa, small ones up to large ones. Okay, sorry, let me show you one more. I think this is a good one. All right, so I want to verify this identity. So they're giving me an identity and asking me to verify it. And sometimes the double angle verifying identity thing can be tricky. This one's not too bad. So here I have 1 plus sine 2 theta equals sine theta plus cosine theta quantity squared. Okay, I need to verify this identity. Now remember, the way we do that is we pick the more complicated side, use our identities that we know to reduce it down to something a little simpler. All right, any ideas? Yeah, I think what we do here is, look, this is squared, so let's take the right-hand side as our more complicated side, and let's square it out. And hopefully, if we do, that will reduce down to 1 plus sine 2 theta. All right, so let's try it. So if I square this out, remember that what I'm saying is sine theta plus cosine theta times sine theta plus cosine theta. So when I do the FOIL method, the first terms you'd have is sine times sine, which is sine squared. Your second term, you're going to have sine theta cosine theta. The inside terms are going to actually be the same thing, sine theta cosine theta. And then lastly, you have cosine squared. Okay, so then if I bring these together, and actually I'm going to bring them together in a clever way, I have sine squared theta plus cosine squared theta. Let me lump my squareds together. And then the middle two terms were the same thing, so when I add them together, I just have 2 sine theta cosine theta, like that. Okay, you may see where this is going, hopefully. I now recognize sine squared plus cosine squared is something we know, right? Pythagorean identity, sine squared plus cosine squared is 1. And 2 sine theta cosine theta wouldn't have meant anything to us before today, but now in today's discussion it does. That is sine 2 theta. And there it is. That's exactly what I was looking for. We have verified the identity. Okay, I hope that makes sense. All right, now Um, Earlier, in example 2, we used a double angle identity to go from 6x down to 3x. Okay, now that's actually a very useful thing. Um, but what about this? What if we wanted to go from 1x to 2x, or theta to 2 theta? And why would we want to do that? Because notice with these double angle identities, the theta term, so the sine thetas, cosine thetas, the tangent thetas, are typically squared. Okay, so maybe I want to get rid of higher powers. And we can do that. We call these the reduction formulas. And all it is, so let me write them out and I'll explain them. So these are my reduction formulas. The first one says that I can write sine squared theta as 1 minus cosine 2 theta all over 2. Let me write the others down and we'll explain how this is nothing actually new. We've already seen this, okay? Cosine squared theta can be written as 1 plus cosine 2 theta all over 2. And then tangent squared, well, for tangent squared, we'll just use the quotient identity. That's sine squared over cosine squared. So I get 1 minus cosine 2 theta over 1 plus cosine 2 theta, like that. Okay, now the question you may have is how did you get this? And that's a good question to have. Alright, so let me just show the sine squared one. The cosine squared follows just the same way. What I'm using here actually is the cosine double angle identity, cosine 2 theta. Remember, in terms of sine, would be 1 minus 2 sine squared theta. Okay, and you do have to memorize these. You have to memorize the double angles, okay? So I have cosine 2 theta equals 1 minus sine 2 sine squared theta. So now if I just solve algebraically for sine squared, all right, so first I'm subtracting 1 from both sides. And then I divide both sides by negative 2. And in doing so, well, look, I get a negative cosine 2 theta plus 1 over 2 equals sine squared. And then negative cosine 2 theta plus 1 is a little bit more awkward than if we just reorder the terms and say 1 minus cosine 2 theta over 2. That's how we get that. Okay, that's how we get it. We're just solving algebraically for sine squared using the double angle identity. And you can see then for cosine squared, that's the same thing. All right, now, why is that useful? Okay, that's a good question. Let me give you an example. All right, and let me know if you have questions, please. Example 5, we want to write cosine to the 4th power of x. All right, so this is the 4th power. We want to write it in terms of first power trig functions. In terms of first power trig functions. So I don't want to deal with cosine to the 4th power. Maybe whatever application I have, that's very difficult. So what I want to do is be able to write this as cosine to the 4th power equals something to the 1st power plus something to the 1st power plus something to the 1st power, maybe, okay? Something like that. And what we're going to do is use our reduction formulas that we just learned, which is again just a reordering of our double angle identities to help reduce the powers. So notice I went from cosine squared to cosine to the 1st power, right? So if I use the reduction formula on cosine to the 4th, maybe I can get it down to cosine squared. Let's see. All right, so we start off with cosine of the 4th x, and what I recognize is that that's cosine squared quantity squared. Agreed? Cosine squared squared is cosine of the 4th. And I'm going to use the reduction formula on cosine squared. So For cosine, remember that's going to be 1 plus cosine 2 theta over 2. So I have 1 plus cosine 2x over 2 quantity squared. Alright, and now what I'm going to do is, and maybe it'd be easier to see if I take out that 2 in the denominator, pull it out first, that's a 1/4 1 plus cosine 2x quantity squared. I think that makes it a little easier to do my algebra that way. Alright, so now when I FOIL out the 1 plus cosine 2x, I have 1/4 times, let's see, 1 plus cosine 2x times 1 plus cosine 2x times 1 gives me 2 cosine 2x, and then plus cosine squared of 2x. Alright, so far so good, but now notice I have a cosine squared 2x, so what can I possibly do there? How about I do the reduction formula again? And what I'm going to do first of all is distribute this 1/4 across, and then I'm going to apply the reduction formula there. So I get 1/4 plus 1/2 cosine 2x plus 1/4 times, well, what's cosine squared of 2x? I'm using my reduction formula, and I'll write it in yellow to make it stand out. We get 1 plus cosine of 2x times 2, right? We are doubling 2x. It gives me a 4x all over 2. And see here, I'll make a note. If we let theta be 2x, then 2 theta is 4x, and that's kind of what we're doing. Alright, and now when I let the dust settle here, let's see, I get 1/4 plus 1/2 cosine 2x plus, what is that, 1/8 times 1 plus cosine 4x. I can clean it up finally. Let me think. So if I distribute the eighth across here, I have 1/8 plus 1/4. 1/4 is the same as 2/4, or 2/8, I mean. So 1/4 is the same as 2/8, so I get 3/8 plus 1/2 cosine 2x plus 1/8 cosine 4x. And there it is. I have now written cosine of the 4th x, which is actually kind of complicated because that's cosine times itself 4 times, and reduced it down to cosines to the first powers, which may be easier to work with. I mean, we at least know what the graph of these type of things look like, right? And so the reduction formulas may be useful in that regard. I hope that makes sense. Alright, now what we're going to do is we're going to switch gears, going from double angle now to half angle. How do I go from theta to theta over 2? Alright, so one way we could do this, or the way we get these, is from the reduction formulas. Let me just write them out, and then we'll see if we can kind of explain them. Alright, so here I'm going to have sine of theta over 2, so this is my half angle identity. What I have to do then is say plus or minus, so it could be plus or minus depending on the context, square root of 1 minus cosine theta over 2. That's my half angle identity for sine. For cosine, it's something very similar. Cosine of theta over 2 equals plus or minus the square root of 1 plus cosine theta over 2. And then tangent, again, we are allowed to apply the quotient identities. So I get plus or minus 1 minus cosine theta over 1 plus cosine theta, all under the square root, like that. Okay, so these are my half angle identities. And where do I get this? So let's look at sine. What I'm doing here is I'm taking the reduction formula, sine squared theta equals 1 minus cosine 2 theta over 2. And so if I replace the theta in sine squared with something over 2, okay, so let's rewrite, let's call this x, and then let's let x be theta over 2. If that's the case, then I get sine squared of theta over 2 equals 1 minus cosine of 2 times theta over 2, which is theta, all over 2, like that. And then I take the square root of both sides, and I get the half angle identity that we were given. Okay, we can do the same thing for cosine, and then for sine, we can get, for tangent, we can get around it a little bit by simply applying the quotient identities. Okay, I hope this makes sense. All right, so then what does that allow us to do? Something like this. So this is example 7 in your text. Let's find sine of 15 degrees. Now, you may remember from last time, we actually did sine of 15 degrees already using, we said 30 degrees, or 45 degrees minus 30 degrees. But here we're going to use the half angle identity. So 15, recognize that, please, as 30 degrees divided by 2. So here I'm trying to find then sine of 30 degrees divided by 2, which is going to be the positive 1 minus cosine 30 degrees all over 2, right? I'm just using my half angle identity here. And it's positive, why? Because 15 degrees is in the first quadrant, right? So now from there it's just some algebra. Cosine of 30 degrees, if you remember, is what? Sine of 30 degrees is 1/2. So cosine of 30 degrees is root 3 over 2, all over 2, all over square root. All right, so then if I get a common denominator in my numerator up here, I'm going to rewrite 1 as 2 over 2. So then I have 2 minus root 3 over 2. Dividing by a fraction is the same as multiplying by its reciprocal. So it's 2 over 1, all in the square root. And then, so I can see now the 2's cancel, and I end up with the square root of 2 minus root 3. And let's see, I think I actually made a mistake here. Yeah, I did. Look, I said dividing by a fraction is the same as multiplying a reciprocal, right? So dividing by 2 is not the same as multiplying by 2. That's silly. It's the same as multiplying by 1 over 2. So they didn't cancel out. And so we end up with, that's in the square root here. In my denominator, I have a 4. So that is the same thing as the square root of 2 minus root 3 all over 2. Yeah, that makes a little bit more sense. I apologize for the error. But hopefully that makes sense to you. Now, when we did this with the plus and minus identities, the sum and difference identities, we got the same answer, just didn't look the same. We got something of a little bit different form, but they are the same thing. Okay, so algebraically, depending on your approach, it may look a little different. Okay, good. Any questions? Hopefully you recovered from our algebraic mistake. Okay, let me show you another thing we can do with half angle identities. And really, from a mathematician's standpoint, this is probably more useful. So here we have example 8. I'm given that tangent alpha is 8 over 15, and alpha is in quadrant 3. So that makes sense why tangent would be positive. Cosine and sine are going to be what? Negative. Here's what I want to do. I want to find A, I want to find sine of alpha over 2. Okay, can I find sine of alpha over 2? All right, so let's think. First of all, if I'm going to use the half angle identity, sine of alpha over 2, this is the one we just used, is going to be 1 minus cosine alpha all over 2, and then plus or minus the square root. We got to figure that out. Okay. Now, how could I do this? How could I figure out cosine alpha given tangent alpha? I could use identities, or I could remember, okay, I'm in the third quadrant, so I have a triangle kind of like this, and tangent is 8/15, so that means opposite over adjacent is 8 over 15. Opposite over adjacent, right, here's alpha. And so if I use Pythagorean theorem, 8 and 15 are actually part of a common triangle. 8 squared plus 15 squared is going to give you 17 squared. So this hypotenuse is 17. Okay, now also, remember, since we're in the third quadrant, maybe it's a good idea to think that this is like a negative 15 and a negative 8. And so when I say 8 over 15, it becomes positive, right? Okay, so then that tells me then the reason we did all this is that cosine alpha, which is opposite over hypotenuse, I'm sorry, adjacent over hypotenuse, is going to be negative 15 over 17. Okay, so there's my cosine alpha. So now when I get back to my calculations, I can say that sine of alpha over 2 is going to be plus or minus the square root of 1 minus a negative 15/17 all over 2. Okay, and let's see, 17/17 plus 15/17 gives me, well, 15 plus 17, you get 32/17 divided by 2, which is the same as multiplying by 1/2. I'm not going to make that mistake again. So I end up with plus or minus the square root of 16/17. Right now, the square root of 16 is 4, so I get plus or minus 4 over root 17. And if I rationalize multiplying by root 17 over root 17, I get plus or minus 4 root 17 over 17, and there is my solution. Okay, now, do I have an idea on if this is going to be positive or negative? All right, so here, because I said plus or minus, so here we got to think, look, if I have a third quadrant angle and I half that, I'm going to be either in the first or second quadrant, right? It could possibly and more than likely be in the second quadrant. Now, why do I say that? Because think about how big, if I rotate over 180 degrees, that's pi, right? If I half pi, I end up here at pi over 2, which is 90 degrees. So if I have a second quadrant angle and half it, I'm going to be in the first quadrant. But the third quadrant angles are too big to half them and still be in the first quadrant. So I know we can reason out. Let's say this, since alpha is in quadrant 3, alpha over 2 has to be in quadrant 2. And so for that reason, I know that sine is going to be simply positive. Cosine is going to be negative. So when I look at cosine, and we have some choices now on well, we're using the half angle identity. I'm thinking double angle. We're going to say plus or minus 1 plus cosine alpha all over 2, square root of that, right? Okay, now I also have already figured out cosine alpha. So I end up with, and I also know, is this going to be positive or negative? I'm in quadrant 2, right? We just said that. So this is going to be negative 1 minus 15/17 is what we had for cosine all over 2. And So it's 1 plus a negative 15 over 17. We get 1 minus 15 seventeenths. All right, so from there we just let the algebra take over. We get, let's see, that's going to be 2 seventeenths over 2, which is 2 seventeenths times 1 half, which gives me negative square root of 1 over 17. And then once you rationalize that, you get root 17 over 17, negative, of course. So you get negative root 17 over 17, and there's my solution for cosine alpha over 2. I hope this makes sense. Okay, I hope this makes sense. Half angle identities, we just got to know them. Okay, the double angle ones, though, are the ones we use more often, and the reduction formulas are very useful as well. All right, now from there, let's move on to section 9.5. And we're going to look at solving some trig equations. So let's see, here's what we've done so far. I'm going to post these notes on Canvas or as a PDF. Let's go ahead and start a little bit of 9.5. And what we're trying to do now is solve some trig equations. We've seen some easy versions of trig equations already that I'll explain. And then from there, kind of go to get more complicated, okay? We're going to get more complicated. All right, so let me just start with the first example. Well, actually, let me go over, there's a little intro in the book that I think is really neat. So this is a guy named Thales of Miletus, and he was an Egyptian mathematician. This is around 625 BC. Okay, what he did is he figured out the height of the Great Pyramids of Egypt by doing this. At the tip of the pyramid, or at a known distance, he stood there with his staff. Let's see, it was more like this. The sun's shining over here, okay, leaving a shadow on the ground, like that. At the tip of the shadow, he put his staff, and it has a shadow of its own, something like that. Okay, and then what he recognized was that if you draw this straight down halfway in the pyramid, I have two triangles now. There's one, and there's this one, and they have the same shape, basically. They are what we call similar triangles. All right, and so by use of similar triangles, Thales calculated the height of the Great Pyramids. Which is pretty cool. All right, now we bring that in to discuss that there are ways. Actually, for Thales' example, you don't have to worry about the angles, except that you're using the fact that they're similar triangles, so they have the same angles. And where that comes in is we're saying here that these two angles are the same, and these two angles are the same, and that would work if the sun's rays are hitting the earth in parallel lines, right? So the sun's so big and so far away that the ray that hit the top of the staff was running parallel to the one that hit the top of the pyramid. Okay. All right, now we're going to look at examples where we're trying to solve equations using trigonometric functions, but do these things show up in the real world? Yes, very much so. Very much so. I mean, there is a reason you're studying trigonometry, okay? So example 1, we want to solve something like this. So again, we're going to start off kind of easy. Solve cosine of theta equals 1/2. All right, now let's think back to what we've talked about already. Is it possible that we already know how to solve this? Well, we do already know how to solve this. What's something you might try? So we might try to do this. Cosine inverse of 1/2 equals theta. And this would be partially correct. If I do cosine inverse, remember cosine inverse only gives me first and second quadrant angles. So this would tell me that theta would be the first quadrant angle that gives you 1/2 for cosine, which is pi over 3. Okay, but what this doesn't tell me is I want all angles that do this. Okay, so we want all theta that do this. And pi over 3 is the correct answer, but it's not the only one. All right, so remember there is a quadrant 3 angle that makes cosine positive 1/2 as well. Okay, so what this gives me, when I did cosine inverse, this actually gave me the reference angle. All right, and so you might think about it this way. Here we have pi over 3, but remember also in quadrant 3, cosine's positive. Not quadrant 3, what am I saying? Quadrant 4, cosine is positive as well. So I want the fourth quadrant angle that has a pi over 3 reference angle, right? So here, what is this angle? And one way we could find that is by saying 2 pi minus the pi over 3 down here in quadrant 4. So that's 6 pi over 3 minus pi over 3. We get 5 pi over 3. So the solutions to my equation. So let's say solutions to cosine theta equals 1/2 are pi over 3 and 5 pi over 3. Actually, let me write it this way. Let me make it a vertical list. We have pi over 3 and 5 pi over 3. That's within the first revolution. But if I keep going, right, if I take an angle that's a lot larger but still has a pi over 3 reference angle, I still have a solution when cosine is 1/2, right? So what do? I can say it this way. I can say pi over 3 and 5 pi over 3 plus some multiple of 2 pi. And so we write it like this, plus 2 pi k. Here, k just being some sort of integer. If k is an integer, and I believe we've used that symbol, but if we haven't, this is the set of integers. So what this means is if I say 5 pi plus 2 pi, that works. Pi over 3 plus 2 pi, that works. Pi over 3 minus 2 pi, that gives me a solution. Pi over 3 plus 4 pi gives me a solution. 5 pi over 3 minus 17 pi, 18 pi gives me a solution. Okay, this gives me a whole bunch of solutions. In fact, an infinite number of solutions. And that is the way we do this. So what I have to do again is first you got to find all your solutions within 2 pi. So the way I did that was cosine inverse will give me 1. It'll give me the first quadrant. But then I also have to remember I need a fourth quadrant answer as well if cosine's going to be positive. And so I can just use the reference angle I have to figure that out. Now for the others, I just add multiples of 2 pi. All right, let me do another example. Let's see if we can figure it out using this strategy. So this is example 2, and here I want to find all solutions to sine t equals 1/2. All solutions to sine t equals 1/2. Okay, so the first thing, think within 2 pi, what quadrants would give me a positive sine value. Okay, so in the first revolution, that angle t could be in quadrant 1 or quadrant 2, right? Quadrant sine is positive in the first and second quadrant. So in my first go around, I need a solution from the first quadrant and a solution from the second quadrant. From the first quadrant, I can just use sine inverse, okay? So if I said t equals sine inverse of 1/2, when does sine become 1/2? At pi over 6. So here, that's my first quadrant solution. If you want to visualize it, here's pi over 6. Now my second quadrant solution, I have a pi over 6 reference angle. So this angle here is found to be how? Or how do you find it? So that's, let me see, let's make some notes. That's quadrant 1. My quadrant 2 is going to be t equals pi minus pi over 6, which gives me 6 pi over 6 minus pi over 6, 5 pi over 6. Those are the two solutions within one revolution that are a solution to this equation, the two angles. The first quadrant, pi over 6, and the second quadrant at 5 pi over 6. Okay, so now to find all of them, so all solutions, you have t equals pi over 6 plus, well, it repeats itself every 2 pi, so 2 pi k. And you could also say 5 pi over 6 repeating itself every 2 pi plus 2 pi k. Here, k being an integer. And I hope this makes sense. So there are my solutions. I hope that makes sense. Now what we'll commonly do is just limit our, we want the solutions just on a certain range. And most of the time, that goes from 0 to 2 pi. Okay, so let me show you some more examples. Now, these two are I said these are our simple examples. They may not feel simple right now, but they're simple in the fact that the equation itself was not very difficult. We didn't really have to solve for anything. But a lot of these trig equations, you have to manipulate it to get it in a form like example 1 and example 2 before you can even begin to solve it. So as a tip, so let me say tip, it may be useful to replace the trig function with an algebraic variable. Why? In order to use algebra to solve for that trig function before we actually solve for the angle. For the trig function. Okay, and we'll do some examples where we have, well, if we do it this way, it'll make things easier on us. Okay, all right, now let me show you some more examples and we'll see if this tip comes up. So example 3, I want to solve 2 cosine theta minus 3 equals a -5, and here I'm going to solve this over the range 0 to 2 pi. So I'm only going one revolution this time. Okay, now let me go and show you what I mean by our tip here. It may be confusing that we have 2 cosine theta minus 3 equals a -5. I don't really know much about cosine in this interval. Okay, now this is just a linear equation in terms of trig. So what I'm going to say here is let's let me get a good variable. How about y to be cosine theta? And so now my equation becomes 2y minus 3 equals a -5. I can solve that pretty easily for y using just basic algebra. that means 2y equals, adding 3 to both sides gives me negative 2. So y equals negative 1. So the question is really asking 2 cosine theta minus 3 equals negative 5 is kind of a goofy way of saying, can I just solve cosine theta equals negative 1? Okay, that's what we're looking for. All right, and from that, I can visualize that. Negative 1 is the low. So when does cosine hit its low? It hits that at pi. And I can think of that in a couple ways. One is I can just visualize the unit circle. Okay, when does, remember your points are cosine theta, sine theta. So when do I have an x coordinate of negative 1? Over here at pi. Pi gives me a negative 1x coordinate. Another way I could think about that is if I simply just graph cosine, starts at 1, it does something like this, right? There's 0, there's 2 pi. What are these other numbers? Well, that's pi. So it hits negative 1 at the value pi. There's two different ways to think about it. Okay, or you can just have memorized the values and just go from there. All right, so there's my solution, theta equals pi. And it's the only solution. Why didn't I do that plus 2k pi thing, or 2 pi k? Is because I only wanted it from 0 to 2 pi. Okay. Let's look at a couple more. I'm going to go over a couple more, and we'll just call it a day from there. And we'll pick up with more of this next week. All right, so example 4. This time I want to solve 2 sine squared minus 1 equals 0. And here I want theta to be between 0 and 2 pi. So again, I'm just doing it over 1 revolution. Okay, now I'm going to do that same trick where I'm going to let sine squared be y. And so now I have 2y minus 1 equals 0, or y equals 1/2. Okay, so that's what I'm trying to figure out. Or in other words, going back to trig, sine squared theta equals 1/2, or sine theta equals, taking the square root of both sides, plus or minus the square root of 1/2, which is what? Plus or minus 1 over root 2, which is plus or minus root 2 over 2. Okay, so there it is. Sine theta equals positive and negative root 2 over 2. Now in this one, I got to think about when is sine positive and when is sine negative. So sine's positive in quadrants 1 and 2, negative in quadrants 3 and 4. So I'm actually have a solution from every quadrant here. And we can think about it. I don't think this one's too hard because when does sine equal root 2 over 2 in the first quadrant? Pi over 4. Okay, from there, just think about your pi over 4 reference angles in each quadrant. So quadrant 2 with a pi over 4 reference angle, what do you have? 3 pi over 4. In quadrant 3, it's 5 pi over 4. And quadrant 4, 7 pi over 4. And there are your solutions. If you want to visualize that, what I just said there, okay, so think in quadrant 1, here I'm at pi over 4. In quadrant 2, in quadrant 2, if I have a pi over 4 reference angle, that means I have a pi minus pi over 4 or 3 pi over 4 angle. And then you can play the same game in quadrants 3 and 4. So there's pi over 4 there, pi over 4 there. So this angle, again, is pi plus pi over 4, which gives you 5 pi over 4. And the last one is 2 pi minus pi over 4, which is 7 pi over 4. And that's how you get your 4 solutions there. All right. Let me show you one more, and then we'll pick up with example 6 next week. Okay. So that's example 4. Example 5, we have solve cosecant, equals -2, going from 0 to 4 pi. So I actually want 2 revolutions this time. Cosecant equals -2, going from 0 to 4 pi. Okay, so what do we do? Well, actually, what I think would be easier here, anytime I see cosecant, I'm going to try to move it to sine. I'm going to use the reciprocal identity, right? So here, if I have cosecant theta equals -2, I know the reciprocal of that, I mean, this is the same thing as saying 1 over sine equals -2, or in other words, sine equals -1/2. Now we're talking. Now we're in a position, or in a common environment, right? This is something that we know. And if I'm thinking sine is -1/2, that would make theta be in what quadrants? 3 and 4. Okay, so what I need to do first is think about what kind of reference angle do I need? All right, so for sine theta to be 1/2, that would mean that theta was, what, pi over 6? Okay, so now I need a quadrant 2 and a quadrant 3 and a quadrant 4 angle with a pi over 6 reference angle. So let me think. So like this. Quadrant 3, here I'm at pi over 6. Quadrant 4, here I'm at pi over 6. So in quadrant 3, that would be pi plus pi over 6, which is, let's see, 6 pi over 6 plus pi over 6, 7 pi over 6. So there's my quadrant 3 angle. My quadrant 4 one is 2 pi minus pi over 6. So that is 12 pi over 6 minus pi over 6. How about 11 pi over 6? Okay. And again, how did I do that? I said quadrant 3. I said pi plus pi over 6. And for quadrant 4, I said 2 pi minus pi over 6. And that's how I got those. Okay, and this is not quite the correct answer. Why is that? Because we wanted to go all the way up to 4 pi. So I don't need just these angles, but I also need going a full revolution and ending up back where I started. So how do I do that? Okay, we'll just say 7 pi over 6 plus 2 pi and 11 pi over 6 plus 2 pi. All right, and those would be, let's see, 7 pi over 6 plus 12 pi over 6 gives me 19 pi over 6. And 11 pi over 6 plus 12 pi over 6 gives me 23 pi over 6. Okay, so my final solutions, let me write it one last time. 7 pi over 6, 11 pi over 6, 19 pi over 6, and 23 pi over 6. And I had to give 4 solutions. Why? Because remember, I started out going from 0 to 4 pi. These two are from 0 to 2 pi. These two are from 2 pi to 4 pi in that range. All right. I hope this makes sense. You have to know your trig values. If you don't know your trig values, this is going to be very, very difficult. Other than that, we're just using a little bit of algebra and then some reasoning. So remember, you can't just memorize your way through these things. You kind of have to do some critical thinking. Hopefully it makes sense though. If not, let me know. Give me some questions. I'd be glad to help. Guys, thanks for watching, and good luck to you, and we'll keep in touch. All right, see you later.